Hi everyone, sorry I can't be there with you today, but what we're going to do right now is we're going to take some notes in our Unit 3 notes packet. So if you could open that up to page 6, we're going to start on this Part 4 Molecular Geometry and Polarity page. So we're going to just start by reviewing some things that you should have gotten out of your lab that we did, the Land of Molecular Compounds lab. So in that lab, what you were looking for was being able to build these molecules in 3 dimensions, bringing them off their 2-dimensional Lewis structures off the page, and then being able to look for some patterns. So if a certain molecule were to have, let's say, 4 atoms attached to the central, with no lone pairs on the central atom, you should have seen that every time you were getting a tetrahedral structure, and this is what it looked like in 3 dimensions. Notice here that these 2 bonds are in the same plane. This atom's moving away from you, which we drew as those dashed lines, and this atom's coming out towards you, which we drew as those solid lines. So we're just going to go through and check for some patterns that you should have noticed from that lab yesterday before I come back to help you fill out this next polar nonpolar column. So the next one was trigonal planar. Hopefully from trigonal planar what you saw was there should be 3 atoms attached to the central one with no lone pairs on the central atom. So everything laid perfectly flat in that plane. Then you had things that were linear. So linear can look a couple of different ways. You can have something that's got 2 atoms attached to the central atom with no lone pairs on the central atom, and that would make it linear. But there's kind of 2 ways that you can have something that's linear. In this example, you have a perfectly symmetrical compound, right? So these 2 atoms are the exact same, but you could have something linear in which your 3 atoms are different. That's fine too. As long as you've got 2 atoms attached with no lone pairs on the central atom, that's also linear. The last thing that's linear, that didn't really come up in your lab, but I did show you an example of it, would be something that only has 2 atoms. So if you have something that's only got 2 atoms attached like that, their only option is to arrange themselves linearly. So just 2 atoms, also linear. The next example was trigonal pyramidal. So for trigonal pyramidals, what you should have seen was there were 3 atoms attached with 1 lone pair on the central atom. And what that did was it essentially took that central atom and it kind of like pushed it up away from the other ones, right? And that's because of the lone pair that's on that central atom. So above your central atom, you have this lone pair of electrons, and that lone pair of electrons carries free negative charge. So it's pushing those other atoms away from it. It's repelling those other atoms because those electrons just want to be free to rotate on the top part of that molecule. Then you could have something that's bent. So same rules apply here for being linear. You could have something that's bent that's got the same atoms on either side or different atoms. Usually it's the same atom though, but you would have seen 2 atoms attached to the central one with 2 lone pairs on that central atom. So just double check your lab from yesterday, make sure you've got, excuse me, this pattern correct. And now we're going to talk about why that's important. So you learned in your 3.7 homework using the gizmo about this idea of something called polarity. Polarity arises from molecular geometries. So molecular geometries determine the polarity of a molecule. In your gizmo, you did see things that were both ionic and molecular. But really, you can only focus on the polarity of something that is molecular. So in order to talk about what polarity is, the first thing we have to do is define what's called a dipole. So what is a dipole? It's a separation of opposite charges, positives and negatives, between 2 ends of a molecule. So what you kind of saw in your gizmo, I'm just going to do this for water. So here's the Lewis structure for water. You got 2 H's, an O with 2 lone pairs attached. These lone pairs are settled above the oxygens just like that. And what you would have seen in your gizmo for this molecule is kind of this upside down Mickey Mouse shape. So you had this end right here, and then your two hydrogens were floating down below it just like this. So let me redraw in that Lewis structure. So this is kind of what you saw. And what you should have noticed was this red part of the molecule, excuse me, this red part of the molecule, according to your key, was telling you that that part of the molecule was negative. And then this blue part of the molecule, what you should have seen there was that that part of the molecule was positive. So you see some separation of charges between your ends of a molecule. But a molecule isn't the only thing that can be polar. You can also have a polar bond. But what does it mean to actually be polar? A polar bond or molecule is one in which electrons are unequally shared. And what this does is it creating partial, come on pen, partial charges. Okay, so couple of keywords here. First keyword, unequally. Second keyword, partial. So if you were to think back to something that's ionic, the whole point of an ionic bond or an ionic compound is you have this complete transfer of electrons. One thing will fully give up while the other thing completely takes, creating those charges in those atoms, making them ions, hence the name ionic compound. But in a molecular compound, we said that our electrons are shared. They both go into these bonds that are created between your different atoms. But it turns out that doesn't always have to be the full story. You could have a covalent molecule, and while your electrons are not totally transferred to one atom in the molecule, they can be partially transferred. It's basically like your atoms are playing tug of war with each other, and one of those atoms is just a little bit stronger, so it pulls the electrons towards itself. But it never actually wins. They're stuck in this permanent tug of war where one atom never fully wins. It can't pull all the electrons towards it, but it can pull a good amount of electron density. So how can you show this? How can you show that your molecules have a partial charge? What we use is yet another Greek symbol. I bet when you thought you started this class, you'd never learned so many Greek symbols. So this one here is called delta. This is lowercase delta, not to be confused with uppercase delta, which is a triangle. We will use that one as well. So this lowercase delta can be used to indicate partial charges. If you have a side of your electron or a side of your molecule that has more electron density, meaning it's pulling the electrons more towards it, that side of your molecule should become partially negatively charged. And that makes sense, right? Because electrons themselves are negative. So if they're pulling electrons towards it, that side of the molecule will be partially negative. So the way that you write that is with a little delta minus sign. So to draw a delta, you can practice these at the top of your page. To draw a delta, it's basically like if you were to draw a curvy S and connect it, you can do it that way. Or it's like if you drew a lowercase d and you put a little hook on the end, that's how you draw a delta. So if one side is going to pull those electrons towards it, that means the other side is going to be left with less electron density. So if you have something that has less electron density, that's going to become partially positive. And the way that you're going to write that is a delta with a plus sign as its superscript. So that's one way you can indicate partial charges. Typically, I will use this method to talk about molecular polarity, so which side of a whole molecule is polar. The other way you could do it is you could draw something called a dipole arrow. So in a dipole arrow, your arrow points towards the more negative side of the molecule. And the back side of your arrow gets crossed to look like a plus sign, which helps you like note that side of your molecule is positive. So if I were to take a look at this molecule right here, HF, you'll see that the left side is electron poor, mean electron deficient, doesn't have as much electron density, whereas the fluorine side is electron rich. It's pulling those electrons towards it. So the way that you would use this to indicate a dipole arrow is you would draw the arrow towards fluorine, which is the stronger atom, the more electronegative atom, and you would cross the end of your arrow like that. So typically I like to use dipole arrows to represent bond polarity, so that way you're not confusing the deltas and the dipole arrows, but honestly, truly, you could use just one method for both and it would be fine. But I'll show you how I use them. So how can you decide if a molecule is polar or not? What you have to do is look at the shape. So like I said earlier, geometry is super important because geometry gives rise to polarity. If you have a molecule that's perfectly symmetric, meaning it's the same across the whole molecule, it's going to be non-polar because there all your charges are evenly distributed. However, if your molecule is asymmetric, there we go. If your molecule is asymmetric, meaning not the same on every side, it's then going to be polar because you are inherently going to have an atom that is more electronegative or more selfish that's going to pull those electrons towards it. So how can you decide which side of a polar molecule is more negative? I kind of already alluded to this, but basically you look for electronegativity. So the more electronegative atom will pull electrons towards it. So let me go back to our water example. If I drew the Lewis structure for water out just like this, one thing you'll notice is that water has these lone pairs that are sitting above it. And if you can quickly start remembering your molecular geometry, this is a molecule that has two atoms attached to the central, two lone pairs, which means this thing is bent. So the way that it looks in 3D space is basically there's two halves to this molecule, and you cut it in half like this. The top half of your molecule, where those electrons lie, those lone pairs lie, that's going to have a super negative charge. You don't even have to think about which atom's more electronegative here, because there's free lone pairs on top of that molecule. So that's going to make the top half of this molecule have that partial negative charge, leaving the bottom half to be partially positive. But what if that didn't happen? What if you didn't have lone pairs on the central atom? What if instead, say you had something that was linear, like cyanic acid, something like this? Well, in this case, you'd have to decide, what's my more electronegative atom here? To figure it out, you can consult this electronegativity table. I have a bunch of these in the classroom that I'll put out in your table buckets. That will be a resource that you'll always have available to you, but for right now, it's also in your notes packet. So here we're trying to decide between hydrogen, carbon, and nitrogen. What's our more electronegative atom? If you take a look at those three on the periodic table, they show up right here. Nitrogen clearly has the highest value for electronegativity, which means it's going to be the one that pulls electron density towards it, making this side of our molecule the partial negative and this side of our molecule the partial positive. So you can use this rule really to help you, like this table, you can use this table to really help you out with bond polarity. With molecular polarity, really what you're looking for to help you out is symmetry. Is it the same on both sides? Is it different? So how can you tell for sure if a bond is polar? So if I were given like the oxygen-hydrogen bonds in water and I wanted to figure out if they're polar or not, hopefully you remember how to do this from the gizmo. Your first step that you're going to do is you're going to find the electronegativity of each atom. Then you're going to subtract the values. And after that, you're going to compare with the table. So in your gizmo, you should have seen, or you should have created a table basically that helps you figure out whether or not a bond is polar or nonpolar based on that difference in electronegativity values. Kind of the general rule. If you look them up on the internet, they actually can vary a little bit, but the general rule is if your electronegativity difference is less than 0.4, it's going to be a nonpolar covalent bond. If your electronegativity difference is between 0.4 and 1.8, this one differs a little bit. 1.8, 1.9 is kind of the general values. Then you'll have a polar covalent bond. If you have an electronegativity difference that's greater than 1.8, typically this means your bond is probably going to be ionic, or it's so incredibly polar that it basically is as strong as an ionic bond. So, I'm going to have you do this practice section right here and this practice section right here. I'm going to walk through one of these examples with you. In the top practice section, what you're really finding is if the bonds are polar or nonpolar by using the electronegativity value differences. Just as a reminder, the more electronegative atom is going to be the one that pulls on electrons more strongly. So that's going to be the one that's going to become partially negative. Don't forget that. The bottom section, this is the one that I'm going to walk you through. For this one, you're putting it all together. You're identifying if the molecule and the bonds are polar or nonpolar. So I'm going to start by taking a look at this one right here. So NH3. So if I'm taking a look at NH3, the first thing I want to figure out is if the bond is polar or not. So I'm looking at an NH bond in this molecule. There's only one type of bond present. So if I go up and I find an NaH on my table, N is 3, hydrogen is 2.1. So 3, I subtract out 2.1, and I'm left with an electronegativity difference of 0.9. This falls in my polar region, which means that the bonds are polar. How do I know which atom is more electronegative? Which one's going to grab that electron density? I look and I see, oh, nitrogen was 3.0. That one's clearly greater. So this is going to be the one that pulls electron density towards it, leaving hydrogen to have that partial positive charge in each of these bonds. So now I've taken care of the bond polarity, but now what I have to do is figure out the molecular polarity. So if I take a look at this molecule, I notice that it is not symmetric. I have 3 atoms attached to the central lone pair, or the central atom, and I have 1 lone pair on that central atom. That tells me that this is trigonopyramidal. This lone pair is sitting on top of the atom, pushing those hydrogens down away from it. So in 3-dimensional space, what it would look like is that nitrogen, 1 hydrogen is in the same plane, 1 hydrogen's getting pushed out towards you, 1's getting pushed away from you, and then the lone pair is sitting on top. So which side of the molecule is going to be more negative? Clearly the one with the full lone pair on it. So what that's going to mean is the top half of my molecule is partially negatively charged. The bottom half of my molecule is partially positively charged. Okay, so your job is to finish the rest of these on the practice sheet, and then I'll post my answer key to Canvas in the resources folder. Check in there, make sure you've got it all filled out, and then you're done with this.